This lesson develops the RC filter as a practical smoothing stage used after a rectifier. We will begin with the physical action of the series resistor and shunt capacitor, then separate the DC and ripple analyses. After deriving the loaded attenuation model, we will analyze an existing filter and complete a design example. Throughout the lesson, remember that a useful design must reduce ripple without causing an unacceptable DC voltage drop or excessive resistor loss. By the end of this lesson, you should be able to explain RC filter action, determine the correct ripple frequency, calculate DC output and ripple output using a loaded model, and select practical resistor and capacitor values for a stated specification. These outcomes combine physical understanding with calculation and design. The final verification is important. Selecting component values is not sufficient unless the predicted DC voltage, ripple, resistor dissipation, and component ratings all satisfy the original requirements. The rectifier output is unidirectional, but it contains two parts. The DC component is the useful average value delivered to the load. Superimposed on it is a periodic AC component called ripple. Ripple produces unwanted output variation and may appear as hum or interference in sensitive circuits. We therefore describe the instantaneous output as the DC value plus a time-varying ripple component. The job of the filter is to reduce that ripple while retaining as much useful DC voltage as practical. It is useful to keep the two output components conceptually separate. The DC component is the average level and is responsible for useful power transfer. The ripple component is the periodic variation around that average. A filter does not simply make ripple smaller at any cost. Increasing the series resistance may improve attenuation, but it also reduces the DC load voltage and wastes power. A sound design therefore balances three objectives: low ripple, adequate DC voltage, and acceptable component loss and heating. The RC filter uses a resistor in series with the rectifier output and a capacitor connected across the load. Because the capacitor and load resistance share the same two nodes, they are in parallel. This topology is often added after a rectifier or after a capacitor input smoothing stage. We will use this same topology for both DC and ripple analysis, but the capacitor behaves differently at zero frequency and at the ripple frequency. At DC, the capacitor is approximately an open circuit, so current flows through the series resistor and the load. The series resistor therefore produces a DC voltage drop. At the ripple frequency, the capacitor reactance is finite and ideally small. The capacitor provides a bypass path for ripple current, while the series resistor opposes that ripple current. The load is part of both analyses. It receives DC power and, at the ripple frequency, it loads the shunt capacitor and changes the actual attenuation. Follow the sequence from input to output. The rectifier first supplies pulsating DC. For the average or DC component, the capacitor behaves approximately as an open circuit, so load current flows through the resistor and load. For the alternating ripple component, the capacitor reactance becomes smaller. Much of the ripple current is then diverted through the capacitor rather than the load. Together, the resistor and capacitor form a frequency-dependent divider, so higher frequency components are attenuated more strongly. Capacitor reactance is inversely proportional to ripple frequency and capacitance. Increasing either one gives the ripple current an easier bypass path. The time domain interpretation is equally useful. When the RC time constant is much larger than the ripple period, the capacitor voltage changes slowly and the output becomes smoother. However, a large resistor is not automatically desirable because the DC load current produces a voltage drop across it. We must always check that this drop remains acceptable. The capacitor responds to the frequency at which rectified pulses repeat, not always to the mains frequency itself. A half-wave rectifier produces one output pulse per input cycle, so its ripple frequency equals the mains frequency. Full-wave center-tapped and bridge rectifiers produce 2 pulses per input cycle, so their ripple frequency is twice the mains frequency. On a 50 Hz supply, that means 50 Hz ripple for half-wave and 100 Hz ripple for full-wave circuits. The higher ripple frequency is easier to attenuate for the same resistor and capacitor. For DC analysis, replace the capacitor by an open circuit. The remaining path contains the series resistor and the load resistance, so the average input voltage is divided between them. This equivalent circuit is the basis for calculating average load voltage and load current. It also makes the design trade-off visible. Increasing the series resistance may improve ripple attenuation, but it also takes a larger share of the available DC voltage. We will quantify that loss on the next slide. The average load voltage follows directly from the voltage divider relation. Dividing that voltage by the load resistance gives the load current, which is also equal to the average input voltage divided by the total series resistance. The resistor voltage drop is load current times resistance. Finally, the resistor power is current squared times resistance. These equations are all DC quantities. They should be evaluated before the ripple calculation because a design that gives excellent attenuation may still fail if it loses too much voltage or overheats the resistor. A simple approximation treats the RC section as an unloaded low-pass divider. It is appropriate when the load resistance is much larger than the series resistor and the capacitor reactance is much smaller than the resistor at the ripple frequency. The magnitude of the transfer function gives the fraction of input ripple appearing at the output. Multiply the input RMS ripple by this magnitude to estimate output RMS ripple. This approximation is useful for insight, but it does not include the effect of a finite load resistance. A more accurate ripple model includes the load. At the ripple frequency, the capacitor and load resistance are in parallel, creating a complex shunt impedance called ZP. That impedance forms a divider with the series resistor. The loaded transfer function is ZP divided by R plus ZP. Multiplying the input RMS ripple by the magnitude of this transfer function gives the output RMS ripple. Use this loaded model whenever the series resistance is not negligible compared with the load resistance. For hand calculation, the complex loaded transfer function can be written as this real-valued magnitude expression. The first squared term contains 1 plus R over RL and represents the influence of loading. The second squared term contains omega RRC and represents frequency-dependent smoothing. A larger denominator means smaller output ripple. This formula predicts ripple attenuation, while the separate DC voltage divider equation predicts average voltage loss. Both calculations are required for a complete design. Ripple factor is the ratio of RMS output ripple to average output voltage. Multiplying that ratio by 100 expresses the result as percentage ripple. Attenuation is the ratio of output ripple to input ripple and equals the transfer function magnitude. A smaller ripple factor means the output is smoother relative to its DC level. A smaller attenuation magnitude means the filter passes less of the incoming ripple. A satisfactory design must meet both the ripple limit and the required average output voltage. A full-wave rectifier on a 50 Hz supply provides 20 volts average and 1.5 volts RMS ripple before the filter. The filter uses 220 ohms, 100 microfarads, and a 2.2 kilo-ohm load. Because the rectifier is full-wave, the ripple frequency is 100 Hz. We must determine the average load voltage, output ripple, ripple factor, and resistor power. The circuit image shown is the original figure from the lesson and has been embedded and changed. Begin with the DC model. Substitute 20 volts, 220 ohms, and 2.2 kilo-ohms into the voltage divider equation. The average load voltage is 18.18 volts. Dividing by 2.2 kilo-ohms gives a load current of 8.26 milliamperes. Notice the physical consequence of the series resistor. Even before we calculate ripple, the available DC output has fallen from 20 volts to 18.18 volts. This voltage loss is the price paid for part of the filtering action. Now calculate the two terms in the loaded attenuation expression. Omega RRC equals 13.82, while 1 plus R over RL equals 1.10. Substitution gives a transfer magnitude of 0.0721. Therefore, about 7.21% of the input ripple reaches the load. Multiplying the 1.5 volt RMS input ripple by this magnitude gives 0.108 volt RMS output ripple. The strong attenuation occurs because the frequency-dependent term is much larger than the loading term. Divide the output RMS ripple by the average load voltage to obtain a ripple factor of 0.00595, or 0.595%. The resistor dissipates about 0.015 watt under steady-state load. A quarter-watt resistor is therefore comfortably adequate for this calculated dissipation, although practical design must also consider surge and voltage rating. The analyzed filter delivers approximately 18.18 volts DC with 0.108 volt RMS ripple. These results are internally consistent and physically reasonable. A bridge rectifier on a 50 Hz supply provides 15 volts average with 2 volts RMS ripple at the filter input. The required output is approximately 12 volts at 40 mA, with RMS ripple not exceeding 0.20 volt. We must choose practical resistor and capacitor values and specify suitable ratings. Because this is a bridge rectifier, the ripple frequency is 100 Hz. The supply diagram shows the final component values, but we will derive and verify them step by step. Convert the output requirement into an equivalent load resistance. Dividing 12 volts by 40 mA gives 300 ohms. This resistance becomes the load value used in both the DC voltage divider calculation and the loaded ripple expression. A quick reverse check confirms that 12 volts across 300 ohms gives 0.040 ampere. Establishing the load resistance first keeps the later design equations consistent with the specified operating point. The series resistor is selected from the allowed average voltage drop. The input average is 15 volts and the desired output is 12 volts, so the resistor may drop 3 volts at 40 mA. Ohm's law gives 75 ohms, which is already a preferred practical value. This choice fixes the DC operating point. We now need to choose the capacitor so that the same resistor also provides enough ripple attenuation at 100 Hz. The allowed transfer magnitude is the output ripple limit divided by the input ripple. Dividing 0.20 volt RMS by 2.0 volts RMS gives 0.10. Therefore, the filter may pass no more than 10% of the incoming ripple. This value is the maximum acceptable magnitude of H. The capacitor must be large enough to make the loaded attenuation equal to or smaller than this target at the 100 Hz ripple frequency. Rearrange the loaded attenuation expression to solve for capacitance. The bridge ripple frequency is 100 Hz, so omega R is 628.3 radians per second. Substitute the maximum transfer magnitude of 0.10, the 75 ohm resistor, and the 300 ohm load. The minimum capacitance is approximately 210 microfarads. Component selection should move upward to the next common value, so choose 220 microfarads. Selecting a larger standard value gives a small attenuation margin. Verification must use the selected standard values, not the unrounded minimum. With 75 ohms and 220 microfarads, the loaded transfer magnitude is 0.0958. The predicted output ripple is therefore 0.192 volt RMS, which is below the 0.20 volt limit. The DC divider gives exactly 12.0 volts at the specified load, and the resistor dissipates 0.12 watt. The chosen values satisfy the voltage, ripple, and steady-state power requirements. The final design uses a 75 ohm resistor rated at half a watt and a 220 microfarad electrolytic capacitor rated at least 25 volts. The calculated resistor dissipation is only 0.12 watt, so the half-watt rating provides useful thermal margin. The capacitor voltage rating must exceed the highest expected voltage, including no load and mains high conditions, and its ripple current rating must also be checked. The predicted output is 12 volts DC with about 0.192 volt RMS ripple, corresponding to 1.6% ripple. Practical RC filter design goes beyond nominal equations. Regulation is poor because changing load current changes the voltage drop across the resistor. Efficiency falls as resistor dissipation increases. The capacitor voltage rating must allow for no load, mains high, and surge conditions, while its ripple current rating must suit the alternating current it carries. Inrush current can be large when the capacitor is initially discharged. Finally, electrolytic capacitance varies with tolerance, temperature, and aging, so worst-case ripple should be checked using the minimum expected capacitance. RC filters are simple, inexpensive, and free of magnetic components. They work well at light load and are useful as an additional smoothing stage. Their main disadvantages are DC voltage loss, poor regulation, and continuous resistor dissipation, which make them unsuitable for high-current supplies. Typical applications include low-current bias supplies, small-signal analog circuits, detector circuits, and post-filter smoothing. Where load current is higher or regulation is important, an LC filter or regulated supply is usually more appropriate. The series resistor opposes ripple current, while the shunt capacitor bypasses much of that ripple around the load. At DC, use the resistor and load as a voltage divider. At the ripple frequency, use the loaded transfer function. Full-wave rectifiers produce ripple at twice the mains frequency, which makes filtering easier. A complete design must satisfy ripple, average voltage, resistor power, capacitor voltage, ripple current, surge, and tolerance requirements. Use the review questions to check whether you can connect the physical action, equations, and practical design choices.